Hello, pre-calculus. Today we're going to be looking at probabilities of what we call independent events. So we looked at something that's similar. We looked at the probability of mutually exclusive events. And mutually exclusive events were um, events that you could sort of separate the outcomes. It's like so that you could add the probabilities, like the probability of getting a 2 or a 4 on this dice. We could do the probability of getting a 2 plus the probability of getting a 4. Although we had some non-mutually exclusive events where they overlapped, like the probability of getting an even number or an odd number. And so we can't just add the probability of getting an even number plus the probability of getting an odd number because there's an overlap. So that was with addition, and that's with the OR statement. We're going to be looking at independent events, and that is when two things have to happen simultaneously. Can we separate those events out? So I'm going to give you an example. If I roll 2 dice, right, and I want to get 2 6s, so I roll 1 dice and the other dice. Now, we looked at the probability of that, but can I separate that into 2 events that have to happen both at the same time? Like, can I roll 1 dice, and does that affect the roll of the other die? And if they don't affect each other, that's called an independent event. Now, I'm just going to put this up here. An independent event, oh gosh, is right here. An independent event. Okay, I wrote this out. If 2 events can be separated into 2 separate experiments where conducting one experiment does not affect the probability of the other, then the events are independent. So we're going to be looking at those kind of events today. Conducting one experiment does not affect the probability of the other. In this case, rolling this dice does not affect the probability of this dice. Wow, I rolled 2 6s. What are the chances of that? Well, here, let's look at the chances of that. Here we have, I've listed out the sample space for this experiment. Find the probability of rolling 2 6s on 2 dice. And so we had this question before, and some people didn't get all of the elements of the sample space. So I organized it so I know that I have 2 dice and I have to look at all the different combinations. So in this case, I have 1 on the first die and 1 on the second die, and 1 on the first die and 2 on the second die, etc. So this is the first die, and this is, wait, no, this is the first die, and this is the second die. So those are all the possibilities, and there are 36 of those. And we can see those, and we have to know that this element right here, like say 3, 2, is a different outcome than 2, 3, although it still looks the same, but this is a 3 on the blue die and a 2 on the red die. So I have red and blue in here. Anyway, if I want to figure out the probability of getting 2 6s, I would just look to see how many elements are in my event 2 6s. So the probability of getting what 6 6 is, there's only one possible way to get 2 6s. That's a 6 on both die. If I switch those around, it'd still be a 6 on both die. So there's just one of those out of 36, so that equals 1 out of 36. Now those are independent events. So what we're going to look today we could write this as the probability of getting a 6 and another 6. So we have this word and that is usually the notation is 6 intersection 6. So and is like an intersection mark. So we want to do that. Okay. Now we're going to just look at this probability in a different way, because writing out all of the elements of the sample space could be kind of tricky, you know, and you might not get them all. What if I wanted to roll 3 dice? Oh my gosh, that would be like a lot in my sample space. I don't want to write that out. So let's see what we can do with independent events. We know this is independent because if I roll 1 die, it does not affect the outcome of the other die. They're just independent. So I could say the probability of this equals the probability of getting a 6 on the first die times the probability of getting a 6 on the second die. Because basically what's going to happen is I'm going to get like So the probability of 6 and 6, if they're independent, is the probability of getting a 6 and then getting a 6 again. So that's multiplication. Now, the reason that's true is that these both events have to happen at the same time. So I have 1/6 probability that it happens once, and then if I want it to happen again, I'm going to have to multiply that by 1/6. So that equals 1/6 times 1/6 is 1/36. So we can see that this little thing works for us if the events are independent. They're independent. So that's it. Most events are independent that we could think of. There's an example on Khan Academy of throwing free throws, and you might have a probability of throwing a free throw is like 75%. So like let's say the probability of making a free throw equals 75%. So what is the probability of you make 5 free throws in a row? Well, you're going to have to say, well, the probability, are these independent? Like, does making a free throw affect the probability of the next free throw? Well, it may, because maybe you gain some confidence, but we have to assume that they're independent. If they are independent, we could say the probability of making 3 in a row, let's just do 3 in a row, would equal 75%, which is 0.75, times another one, 0.75, times another one, 0.75. You have to make all 3 of them in a row, so you'd multiply that out, and whatever that is would be your probability. It's going to be less than 75%. What is that? 0.75. Now you could just raise that to the third power, because it just has to happen all simultaneously. It's like you're multiplying those out. So this is 0.42 rounded off. So it's probably 0.42 or 42%. And so that's approximately. Okay, well, what's the probability of missing 3? Probability of missing 3. 3 in a row. Well, the probability of missing 3 in a row, well, gee, if there's a 75% chance I make it, then there's a 25% chance I miss it. And we could think about that as a 1 minus 0.75, because if that's called a complementary event, we just have to know that a little bit today. But if I subtract my probability from 1, I get the probability of the complement. What's the probability that it doesn't happen? And I would raise that to the third power because it has to happen 3 times in a row. So that equals 0.25 probability of missing, and it has to happen 3 times in a row. So that's 0.25 raised to the third power. It is 0.156. So that's approximately 1.6%. That's pretty low. That's approximately 1.6, percent. Or wait, that was 0.0156, which rounds off to that. So this is what we have. Let's see, 0.75 raised to the third power, just to double check that one, was, 40. Okay, anyway, so there's not a very good chance I missed 3 in a row, I guess. Anyway, let's look at another sort of example with cards, because this might be an example where we wouldn't have independent events depending on how we do this. So I have just 5 cards here, and what if I just shuffled them up? What's the probability of getting an ace? Well, that would be, there's 2 aces, right? So 2 out of 5. So I pull a card and it's not an ace. So well, I had a probability of 2 out of 5 to get an ace. Well, what's the probability of getting 2 aces? Now, this is where we have to think about how we set up our probability, because if I just do this experiment and separate it into 2 equal probabilities, I would like draw 1 card, and then I would have to put it back in to draw the next one to make it 2/5 again. So let's just look at this again. So if I had to find the probability of getting 2 aces, I could write this out. These are all the combinations. And so I have this one would be the first card, and this one would be the second card. And I just go, okay, let's see, what's the probability? And so these are all the combinations. And now there's a black ace and there's a red ace in there. And so I have them in there. And what's the probability of getting two aces? Well, one of the things I can do is I can say, well, let's just put it back after the first draw, because then the two probabilities would be the same. So the probability of getting, let's see, ace, ace would equal the probability of getting an ace on the first one times the probability of getting an ace on the second one. So that would equal 2 out of 5 times 2 out of 5, which equals 4 out of 25. Okay, 4 out of 25, that's my probability. If I look in my table here, I might notice that these 4 boxes have 2 aces, and there's 25 different possibilities. So that gives me an easy way to find a probability without having to draw this complicated sample space. But if I did it without replacement, then things change a little bit, because conducting the first experiment, like drawing one card, changes the probability of me getting an ace on the second card, because I only have 4 cards left. So there might be, I don't know, and I don't know how many of those are aces. So conducting the experiment once affects the probability of the second time. So if I wanted to find the probability of getting 2 aces, and I didn't replace it, I just went like this, and then I went like this, 2 aces. What's the probability of getting 2 aces? Well, I really thought it was going to be 2 aces. But anyway, how would we do that in our table? Well, one thing we can do is say, we can't get 2 of a kind because there's only one black ace in there. So I can't, if I did it without replacement, I would have to eliminate the ones along this column. So I'm just going to do that. Now, this probability is not one we're going to have to do today. I'm just showing you that this would really change the probabilities. So we have the probability of getting 2 aces now is eliminated to 2 on the top. So we have the probability, let's write it this way, 2 aces equals, there's 2 cases where we have 2 aces. We have an ace on the first card and a red ace on the first card, a black ace on the second card, and vice versa. So we have 2 possible cases where we have 2 aces, and we're not going to use these. So if we count up the rest of them, there's 4 in each row times 5, there's 20. So 2 out of 20, which is 1/10. So this probability definitely changed, okay? So this one right here on the left is the independent events that we need. These are independent, because we put it back. Now, I'm just going to say this. I'm going to assign a Khan Academy. And you don't really have to decide whether the event is independent or dependent. You just have to know, because it says ahead of time that it's independent. So you just have to know that you have to multiply those probabilities to get your answer. And occasionally, you might have to take the complement of the event, to get it right. But anyway, 2 things have to happen simultaneously, so we multiply probabilities. Pretty simple concept. I hope this helps you today, and good luck on the Khan Academy.